Bismillahirrahmanirrahim. Greetings. In the previous video lecture that I uploaded about 2 weeks ago, November 15, I discussed the concept of completing a square. The lecture was at the basic algebra level, and they showed that how the completing a square, the concept of completing a square, led us to an explicit, refined formula that is known as quadratic formula. Now, quadratic formula that you are already familiar with, I have already also discussed it, that I may also go briefly over them when I start the body part of this lecture, uses the coefficients of the unknown to determine the value of the unknown, and use only operation of addition, subtraction, multiplication, division, and extraction of root. And that interests mathematicians. Can they do the same thing for polynomials of degree 3, 4, 5 and higher? And the most aim of the mathematician was to seek to find the roots, the zeros of polynomial. Now, I am using the word polynomial, the zeros, the roots, the degree of polynomial, that I have not defined them yet. These vocabularies are familiar for a college algebra students, but may not be for a basic algebra. So I go over them also, I define them, and then I also go through to the basic algebra level, to the Vieta formula, if I'm pronouncing his name right, a French mathematician, and also at the end give some history about the subject, going to Galois and Abel, and why degree of 5 and higher we could not have a general formula. So I go and start with the summary, if I may, and continue. And this video will not be too long. So I go briefly on that, how we did, we completed the square of taking half of the coefficient of x, square it, add and subtract. Now, I didn't, because we are dealing with equality, which means we are looking for those values of x, that if we substitute for x, that becomes 0. Since we are working with equality, I could say that you can add to both sides half of the square root of, half of the coefficient of x squared. But that may cause a little bit difficulty, because some students, they forget that they have factor a out. That could cause a bit problem for the beginner. And second one is that sometimes when we go to parabola, we don't have equality, it's not equal to 0. We have to complete the square, and that helps a lot to for the sketch of the graph of parabola. And so there is no two sides that we say, okay, we add to both sides. So there is only one side. So it's good to get into the habit of saying that take half of the coefficient of x, square it, whatever that comes out to be, add and subtract. So when you are adding and subtracting same thing, you are not changing what was given to you, the original. And if you have written your expression in this form, in descending form, then the first two, when you complete the square, almost 100% give you a complete square. That's exactly what it gets its name for. And then I have gone through this one. You are already familiar from the previous video, so I'm not going to go too detail on that. Then I go only one other one for those of you maybe wants to take a note. It's just algebraic manipulation in reality that we are doing to come up with that. Now here I take, after that, I completed and did algebraic manipulation and take everything to one side and the other side of the equation. I came out to this stage, and in this stage I took a square root of both sides. Now when I'm taking a square root, most of the time we are taking principal square root. That's what most of the time we are talking about. But in this case, it's not principal square root. This is the two possibilities that we are taking at. So it's a regular square root of 4. Again, in the other table, I have already explained that one. And by doing that, we come up to this refined and explicit formula. And look at this formula. It's using A, B, C, and he's using addition, subtraction, multiplication, division, and extraction of root, and by doing that, the value of x is unknown, is determined. Very, very interesting. Now, it is, as I said, I already mentioned that it did interest mathematicians, so I will go over that also. Right now, let me define for you the concept of polynomial. What is polynomial, and I go briefly on that. And I intend to put a video about at the college algebra level about this subject that is kind of more advanced. And hopefully that video may come soon. Okay, now polynomial is an algebraic expression in this form. So I have written, because addition is commutative, it's good to write it in the form of kind of descending order. And this is called leading coefficient, this is called leading term, this is called degree of the polynomial, and degree of polynomial is always, always, always a non-negative integer. So whole number plus 0. So it's 0, 1, 2, 3, 4, 5, 6, and so on. So the degree of polynomial cannot be a fraction, non-integer fraction, cannot be a real number like a square root of 2 or pi. But the coefficient, they can be. They can take any value of a real number or even complex. But that is, again, when I go to college algebra, I go in more detail of that. So this expression, and then what is algebraic expression? Algebraic expression is if we have constant and variables and glue them together using elementary operation, what comes out of it, addition, subtraction, multiplication, division, what comes out of it, we call it algebraic expression. Like 4 is not algebraic expression because there is no variable involved with that. It's not adding to that. 4 plus 3 is not algebraic expression. But 4x plus 7 is an algebraic expression. Now, polynomial is this, that what I said, that when you make polynomial function, as you are already familiar with the name function, it just function takes over. Now, the value of x will be what will be arbitrarily in a sense. X that will be independent variable in a sense. So it's not only a finite number and that we study about the root of the polynomial. And then a polynomial equation is the same, this expression, if we set it equal to 0. And when we are looking for, excuse me, when we are looking for the value of x that makes this expression true, which is a conditional statement, makes it equal to 0, they are called zeros of polynomial. They are called roots of polynomial. So we are now familiar with polynomial. Now, let me go now to next is about a polynomial of degree 3 and 4 and 5. Again, I'm doing that at the basic algebra level, so I'm kind of waving my hand and don't go too deep into that. Okay, here I have a polynomial of degree 3. This is called leading term, this is called leading coefficient, and this is called degree. Degree is 3. This is called, I have written for you if you want to write it, and this is called a polynomial of degree 4, and this is called a polynomial of degree 5. so I didn't need to continue. They use an and the n because the alphabet numbers are 26, they're finite, the n, but when you use n can be going for 100, 200 or whatever you wish to do it, to go through that. Okay, this is called polynomial of degree 5. Now I go to see what we may notice about the roots of polynomial and what the so-called the Vieta formula comes from, or Vieta law in a sense. Now, what you have to do, a student should be trained really to use examples and the material that they already know to learn about something that they do not know. So they learn about something that they do not know by using what they do know. Now here, I made my own example. I made on my own example, and this example is I use the distributive law, and I end up with these two. These two are equivalent. Now these two are factors, and this is the term. The term. There are three terms in this case. The term of this, but they're equivalent. Like 6, if you write it 2 times 3, 2 and 3 are the factors of 6. But if you write 2 plus 4, 2 and 4 are becoming terms. So these are terms, this is, but 6 is 6, either if you write 2 plus 4 or if you write 2 times 3. Now, here, if I put for x2, this factor becomes 0, and that 0 kill this factor, and that end up to 0, therefore I got one of the zeros of my polynomial. Therefore one of the two roots or zeros, both of them they are used interchangeably, or one of them is 2 and the other one is 3. You can see that. So if you put 2 here you get 0, if you put 3 here you get 0, and same is true here because they are same thing. Now I change it and I go now to another to see if what I can get here. Now here, the 0 of this polynomial is negative 2. And the 0 of this polynomial is negative 3. You can see that, huh? Very similar to the previous one. Now what I notice, what do you notice at that? I notice that, look at this one. The roots are what? 2 and 3, is that right? If I add the two roots, I end up with 5, but this is minus 5. So is there any relation between the roots and the coefficient of x when I am adding that? So I get the feeling that there is a relation. And I come to another example, and again, both of them are negative. I add them, negative 5, but this is positive 5. So I get the impression that when I add the roots of them, of the polynomial, when I add them, then is equal to the negative of the coefficient of x. Whatever coefficient of x is negative of that. But 2 examples, of course, is not enough. I can make more possibility with 1 positive, 1 negative, and so on, and I encourage you to do that. And you end up to be, yes, this is the case in fact. And one other thing that I notice here is that when I multiply the two roots, which is 2 times 3, I get 6. The constant term of the polynomial of degree 2. And when I multiply these two, again I get 6. You notice that? So the product of the roots ends up to be the constant term. Is this the case? I like you do more the different kind of problems you make for yourself, and you said if this is the case or not. And to be a little ahead of you, I say yeah, it is in this the case. Okay, now let me go to another one. Now for a curious student, this is a basic algebra level, they can do that, is to make now a polynomial of degree 3. So make your own polynomial, because you know what the roots are, and that can help you a lot to determine that. Huh? Now I go to this one. Now here, I made the same example, x minus 2, x minus 3, and then x minus 5. I know what the roots of this polynomial are, is 2 and 3 and 5. And I notice that if I add them, 2 plus 3, 5, and 5 is 10. And look at that, I get negative 10. So you add the roots negative with, you change the sign to the negative, you end up to the what, to the coefficient of the one term after the leading term, which in this case is this term. Do you follow me? And when I multiply them together, look at that. 2 times 3 is 6, 6 times 5 is 30, but this is negative 30. Previously I got positive, this time I got negative. So I feel I get the feeling that the sign of them are alternating. So it's positive, negative, positive, negative. Is it true or not? I need more examples to make with different variety of signs and see if this is the case or not. Then I may even go further. And again, this is at basic algebra level. You can do this very easily. You can add another factor to that and then multiply them all together and put it in the term form and see if the addition of the roots end up to be the coefficient of the term that is after the leading term, and if the product of them end up to be the constant term of the polynomial, and then also what happens in between. I like you do it yourself and see. It's not the very top mathematics, it's not looking for the roots of the polynomial of degree 5 or higher. It's something that is known. It's called Vieta, if I'm pronouncing it correct, Vieta law or Vieta formula, and it was known long ago, centuries ago. It's not something a good high school student that they have been trained to have that kind of eye observation and pattern seeking. They may also notice that what is the relation of roots of the polynomial to each term of that polynomial, of any degree, in fact. Okay, now I have that and that. Yes, I am now finished with this. Yes, I am. Now what I do, I go to polynomial of degree 3 and degree 4. The formula that they found for polynomial of degree 3 is about two line of a textbook long. So it's a little bit difficult to memorize it, but it's much better than if you go to for the formula of degree 4, which is almost takes 1 page of the textbook, and it's very difficult and also not even practical for students to memorize it. But a teacher may give them a copy of the formula and then say, okay, find the roots of that using that formula, which is excellent homework or exercise to do. But anyhow, now I go and zoom it and talk about the history background of that, if I may. So as I already mentioned, the formula for degree 3 and degree 4 polynomial was determined. What do I mean by formula? Explicit formula, refined formula that can use only arithmetic operation and extraction of root to give you the roots of the polynomial, the zeros of the polynomial. So it was set up. Then comes to degree 5, and then mathematicians were stuck with that. And they were working and working, and there was one Norwegian mathematician by the name Abel. He found the formula for degree 5, or at least he thought he found it, and he published it. And when you publish, something new, it goes through prominent mathematicians of the time, and they examine it before they publish it. So he passed that FDA test, and then also other mathematicians, they look at that with a magnifying glass to see if they can find any hole in that proof. And again, they haven't found. It was Abel himself who found out that his formula is not correct. There is a hole in that. I strongly believe that he may came up with a counterexample. What I mean by counterexample, he may have end up with showing that, okay, this formula that I got works for this and this and this polynomial, but is not going for this one. So one single it didn't work, that's enough. Then you can use the counterpositive elementary logic. If P, then Q. If not Q, then not P. Therefore, he came to the idea that what about if there is no general formula that works for all polynomials? And that motivated him, and he did prove it. He did prove that, but it was a tragedy that at the early age, is about mid of 20s, he died, and but tuberculosis disease. And then few years later, 5 or 6 years later, another mathematician from France by the name Everest, if I'm pronouncing his first name, Galois, is known more by Galois. And he was a teenage mathematician. He was extremely gifted, and in his late age, and he didn't have any college kind of training for mathematics. And he came with fascinating idea to go through that one. The proof that Abel has given has already been settled. So he was not going to argue and say, okay, there is something wrong with your proof. But what he did, he gave reason why the degree 2 and 3, 2, 3, and 4, there is formula. So how did he do that? He went through the roots of the polynomial and permutation of them, and then they call it automorphism, and to find isomorphism, the similarity in similarity that they had, and then set up a symmetric, what is a group of symmetry of the roots. And he showed that the roots of the polynomial of degree 3 and 4 are kind of disciplined. They follow certain of pattern, and that is the reason there is a formula for them. And when you go to degree 5, then let's start with the degree 5, which is called quantic, another name for that. When he went to degree 5 of polynomial, then the roots started to behave chaotically. There was chaotic in them, so there was no kind of discipline following that. So one reason, and the second reason, the second way that Galois did different than Abel is that he said, hey, you give me a polynomial of degree 5, and I can tell you whether it is solvable by radical or not. So in other words, the whole entire polynomial of degree 5 were classified, that some are solvable by radical, some are not, and the Galois tell you which one are not, which was very fascinating. And how he did, as I have already mentioned it, he went through the roots of them, a group of symmetry, and then automorphism and isomorphism. Automorphism is a function that he used, and isomorphism is similarity that he got. They have same similarity between them. And that goes to the concept of Galois group and Galois theory that is presented in abstract algebra, modern algebra, which is a kind of a very ugly and bitter subject for those students that they are not mathematically inclined, and is very, very interesting and sweet subject for those that they are mathematically inclined. They have the good, natural ability in that mathematics. Now, the other thing I would like to mention is that some student may ask, is there any other way we can do that? Why should we use only operation of addition, subtraction, multiplication, division? Is there any other way, calculus method or something we can find it? The answer is yes. There is the numerical method, and there is also calculus analytical method that Newton is one of them, Newton's technique, that if you take calculus, there is one topic about that subject, that they get as close as you wish to the root. You may not hit the root, that you can get as close as you wish. For example, you say, give me an epsilon, no matter how small it is, 0.000000001, and I can get closer than that number to the actual root. Now, the question comes is that they may not get the root exactly, but we cannot be that much precise. We are happy. and with that, and it's more efficient, much faster, and you don't have to go 1 page or 1.5 page formula to find the roots, that it does it much faster technique. So then the question is that some student may ask is that why the mathematicians were working for decades on this subject and wasting their time. Why don't we just use calculus technique that he gives us the answer much quicker, much faster, more efficient? And why are we wasting my time? Why did they waste their time? Why didn't use their intellectual, gifted mathematics ability to do something better? No, I have 2 or 3 answers to this question. Number 1 is that why people climb to go to the tip of the mountain Everest, that unfortunately some of them they never made it and they died on the way, fall down or what have you. And why don't they take helicopter, and helicopter can go up and land on the peak of the mountain Everest, and then they can bring cup of coffee and take some picture and then come back, the helicopter give them right back. Think about it. That's one answer. Second answer is that is the passion, is the persevere of the mathematicians, that is like an artist that he loves his art and he wants to enhance it each time and get the best possible, the drawing. Same is true with mathematicians. They are kind of, that is their hobby, that is their passion, and they follow it. That is second reason. And the third reason, which is the most important one, is that at the time that they were doing that, possibly they never thought that it will have application few hundred years later. Or no, this same concept of a polynomial of degree 2 and then becoming interested to find the roots of polynomial degree 3, 4 and so on, he gave birth to a new ocean that is called modern algebra or abstract algebra. And in that they go to group theory, they go to ring and field, and then Galois group and Galois proof of this comes almost to the end of the textbook in a sense. And if you are taking undergraduate or graduate, it's almost 2 semester work. And at the end you go through that. So you have to have so much knowledge in order to comprehend how the Galois presented his argument about the different polynomial of degree 5. Some of them they can have solutions, some of them they cannot have. So it's very interesting history it has behind that. And the other thing I would like to relate to answer about this question that was raised is that there is a river in some part of Russia, I forgot the name of it, that there are 7 bridges in there. And people were walking and maybe exercising, and they came to the idea that is there anybody that can pass, that cross each bridge one time only and end up to the same place that he has started with. So they tried and nobody came to that solution. And they even put it in the, in the drawing, and they tried to do it with a pencil and pen, and still they didn't. So this problem was given to Euler, and that gave birth to a graph theory and to the subject of topology in mathematics, which is an ocean of its own. So my point is something that is very minor and is a drop in the ocean that can lead us to find out the ocean of that. So you can say that mathematicians wasted their time, or why did they do that, that I can do it other way much easier. So each of them, they have their own benefit in their own right. Okay, then I am intending to give more video lectures geared to this subject, but at the college algebra level, and those videos that can also help for students that they're taking abstract algebra, so that they know what is the goal and what is the aim and what is this and that. It does help them, yes. and then hopefully if the time permit and I can enhance my knowledge further, I may also go through the whole entire abstract algebra, but aim to Galois group theory only. So those that are related only I like to cover. Okay then, I wish you all happiness and prosperity, and until more coming videos, so long. Bye bye.